I'm Wolf McNally, lead researcher for Blockchain Commons, and I'm going to share my screen here in a moment here and show you a couple things we've been doing in our with our UR specification, which is definitely one of our more popular specifications. This is our research repo on GitHub, and this is a BCR that stands for Blockchain Commons Research. So these papers we consider to be research, not standards. And that's something we can't emphasize enough because, they're still fluid in many cases. We hope that, and we'll have more to say about this later in our Gordian Developer Meeting. This is taking place soon. So, this is actually, it doesn't stop people from adopting it. We encourage people to adopt it and translate these things. Uniform resources are a way of encoding data in a way that's very friendly for transmission as either URI, because they are URIs, or QR, or encode them in QR codes. And I'm not going to go over this text too much because those of you familiar with it already understand URs to a certain extent, but I encourage you to read the document if you're not familiar with it. But our goals, transport binary data of arbitrary content and length using a sequence of one or more URIs or QR codes. And we're going to be talking about that a lot, the sequence of one or more specifically. And our other things here. And then you asked Christopher about implementations. We have our own two primary implementations, URKit for Swift and BCUR for C++. We also, we actually don't have our own Rust implementation. We have a thin layer on top of that, but there is a Rust implementation from a third party, which we are actually using in our Rust stack now. So we definitely appreciate when the community basically takes these things and decides they're valuable and chooses to implement them. And what we're going to be talking about is that implementation step, because even though this document goes on to discuss, how the rationale for URs and examples of how they're encoded and so on, and then it does talk about what a UR looks like, gives examples, and then talks about how a multi-part UR looks like, including this SEQ, which is a part number one, one out of whatever, or X out of Y, and it mentions that the sequence numbers can go higher, 11 out of 10. What does that mean? Well, that basically means that you've gone into the area of rateless fountain codes as opposed to fixed rate codes. And we'll talk more about that in a minute. But this document itself stops short of actually telling you how to implement those rateless fountain codes and so on, and refers you to the new document, the Multipart UR or MUR implementation guide. And that's mostly what we're going to talk about. And if you don't want to understand, there's also the Q&A section here. Why didn't we do things other ways? So we do feel like there's sufficient justification for UR, and a lot of people appear to be agreeing with us. So we're very happy about this. But we have received a fair amount of feedback that people who are going through the source code, because this document used to basically refer you to the source code for implementation of everything else, that we felt that we got enough feedback from the community that said, yeah, we need something that is a better guide for implementers. And so we're going to pop over to the MUR implementation guide. And I'm going to kind of walk through this. I'm going to read to you a little bit, but I hope to gloss over certain sections as well, because I want to give you the flavor for this. And there is source code in here. There is extracts from the Swift source code, but you can think of it like pseudocode if you don't know Swift very well. So that's definitely not a requirement. So as this says, the document does not deal with the encoding of URs generally, and specifically does not deal with their textual representation. That's the job of the other document we were just looking at. It strictly deals only with the partitioning of a message into multiple parts and the binary representation and serialization of those parts. While the multi-part architecture described here can be used to encode single-part messages as a degenerate case when using URs, the single-part syntax that you saw in the other document in the UR specification is required for single-part messages. So this document is intended to be read through from top to bottom, since later sections build on earlier ones. And so implementers and other interested parties who just want to understand the architecture of the system can read that in that way. And then it's a reference for implementation. But you can also, we recommend that implementers also use the top to bottom approach, because you can generally implement these things from the top down, because the dependencies always flow upwards in this document, or at least that's the intent. So just a little bit of terminology here, because you'll hear these used a lot. The message is the actual binary structure that we're going to be encoded and recovering. A fragment is a piece of that message. Fragments are received by the decoder and reassembled. And then a part refers to one of a set of structures encoded for transmission, each of which contains a fragment of the message and metadata needed by the decoder. And in the case of rateless codes, and I'll explain what those are in a minute, more than one fragment may be mixed together in a single part using XOR. Parts containing a single fragment are called simple parts, and parts containing multiple fragments XORed together are called mixed parts. Okay, so those are essential terms because parts can contain more than one fragment uh, XORed together. And what, how does that make sense? Well, you'll see as we explore this. So then we go into discussion of channel types because we really want people to understand the motivation behind this and also why we haven't taken certain other kind of what I would consider more naive approaches. So I talk about the dimensionality of a channel, whether it's full duplex, both people can talk at the same time, half duplex, or simplex, which is actually the term for what QR codes are, where there's a sender that can only transmit and the receiver can only receive. You can think of the QR code on your screen or printed on paper as just a sender, never a receiver. That makes sense, right? Reliability. Okay, so a channel is either reliable or unreliable. Erasure, which basically means the receiver will know they didn't receive something correctly, or reliable deletion, which means they may not receive everything and they won't even know it. So, and this becomes important later. And then ordering. Channels can be either ordered, where everything that goes in comes out in the same order, or unordered. And so generally you start with more primitive kinds of channels and you build these capabilities on top of that. So examples that you're familiar with would be like TCP/IP, which is full duplex, reliable, and ordered. We use that all the time, every time we connect to a website. And then there's UDP/IP, which is what TCP is built on, which is full duplex, but unreliable deletion, which means the receiver won't, delivery is best effort, which basically means packets can get dropped and the receiver will never know it in any kind of inbuilt way. And it's also unordered. Packets can arrive out of order. So when you scan a single QR code, what's that? Well, that's simplex, as we discussed. It's unreliable erasure. So if you try to scan a QR code and it doesn't work, you'll know it, right? So that's an erasure channel. And it's also ordered because when you scan a single QR code, it either arrives or it doesn't, and then everything in it is in the order that it was in the QR code. So that's an ordered channel. But what happens when you animate QR codes? You get a simplex channel that's unreliable, but it's a deletion channel because if there's a series of QR codes going by quickly, you're not necessarily going to know one was failed to read. And so you have to assume that the camera would just miss it and not even know it was trying to read a QR code in that moment. Maybe the camera moved away and QR codes flew by or whatever. And that also means that no matter what you do, the data may arrive in out of order. So we have to deal with this kind of channel. So it's this last form of channel for which we wish to provide a robust solution. So this leads to the discussion of QR code partitioning. So in the case of air gap data transmission using QR codes, it's often desirable to transmit a message that is larger than can fit into a single QR code. And PSBTs is a perfect example of that, which is partially signed Bitcoin transactions for anyone not familiar with that term. In this case, the message may be broken into a sequence of smaller fragments, each of which is transmitted in a separate QR code called a part. The fragments are then reassembled by the receiver to reconstruct the original message. And this requires that each part, in addition to its payload fragment, has to contain metadata with the length of the sequence and its index within the sequence. And that allows the receiver to know when it has received all the fragments and enables it to assemble them in order, thus turning the unordered channel into an ordered one. Remember, I talked about how you build more reliable channels on top of less reliable channels. Okay, so now let's talk about what we mean by fixed rate and rateless. The decision how you break the message into fragments depends on the reliability of the channel. If the channel is reliable, then you can just show each QR code once and be done, right? Because you can do each QR code as a packet. But if the channel is unreliable, then you may have to retransmit the sequence fragments repeatedly so the receiver can reconstruct the original message by eventually receiving all the fragments. And this might be the case if the QR codes are displayed as an animation on a screen. And I also mentioned that if they're printed on a single page, you can consider that to be just everything's there. You can scan it until everything's read, and you don't have to worry about repeating the sequence because it's all there right in front of you. But in case of an animated QR code, yeah, you could have to repeat the whole sequence over and over again. These are called fixed rate options because the number of fragments is fixed, and every part, each containing a unique fragment, must be received to reconstruct the original message, no more, no less. So unfortunately, the problem is with fixed rate codes, you can get stalling, which is where codes are missed and the camera misses them or is blur, refocusing or whatever. And when a code is missed, the receiver has to wait for the entire sequence to cycle through again. And there have been a number of naive approaches that use this. So the problem is that that ultimately this results in divergence from the optimal transition time as more and more cycles to the entire sequence are needed to successfully capture all the codes. So what's the alternative? Rateless codes, on the other hand, are designed to be more robust against such issues and help in converging towards optimal transmission time. In a rateless system, each code is somewhat independent and contains some of the overall message encoded in such a way that any sufficiently large set of codes can be used to reconstruct the entire message. This means that even if some codes are missed, as long as enough other codes are successfully read, the message can still be reconstructed. And there's no specific sequence that needs to be followed, and each code has a relatively high probability of bringing new information to the table that the reader doesn't have yet. This property significantly reduces the likelihood of stalling, as the receiver doesn't have to wait for a specific code containing a specific fragment to come around again in a sequence. The more codes that are read, the closer the receiver gets to having enough information to reconstruct the original message. And the takeaway is this leads to a system that tends to converge towards the optimal transmission time, regardless of individual code losses. And if you think there might be like overhead, well, yeah, there's some overhead. In a well-designed rate system, the number of codes that must be captured is not much higher than the number of fixed rate codes that would be required. So there is some overhead to a rateless system, but because it's an unreliable channel, it actually works out better. So fountain codes, you'll hear that term a lot, are a type of rateless code because it's named by analogy to a water fountain. The flow of water from the fountain is continuous and effectively never ending, but you only need to take a little bit to get a drink. All right. So MUR, the multipart UR scheme, uses a hybrid strategy of both fixed rate and rateless fountain codes. So you actually get the best of both worlds. The message is broken into sec-lane fragments, and that's how many fragments you have. You'll see the term sequence length or sec-lane. The first sec-lane parts of the message are fixed rate and can be, by themselves, be used to reconstruct the original message. So if it takes 10 fragments, you get 10. The first 10 parts that are received are just the original message. If the channel is reliable, like a printed page, then these initial parts are all that need to be generated. Each part generated includes metadata that includes sec-lane, which is the number of fragments in the message, and sec-num, which is the one-based index of the part. The receiver can use this metadata to know that it has received all the parts and to reconstruct the original message in order, even if the codes are scanned out of order. The fixed rate parts have a sec-num less than or equal to sec-lane. You saw that before in the SEQ in the other document. So 10 part QR 10-part sequence, you get 1 of 10 through 10 of 10. If the channel is unreliable, then our system, when requested to generate parts where sec-num is greater than sec-lane, will generate rateless parts. So values like 11 out of 10 are up are normal and indicate rateless codes. This indeterminate length stream of rateless parts are generated using an algorithm that in each generated part mixes together a subset of the entire set of fragments of the original message. And we'll talk about that in a minute. So there has to be a consensus way of dealing with this, and we'll talk about that in a minute. For the sender receiver need to agree on which fragments are mixed into each part. This is done using a consensus stack, and we'll talk about that. Now, so the next section is the consensus stack. Several components in this section are shared by the encoder and decoder and used by them to agree on which fragments are mixed into which parts. In the following subsections, we're going to introduce and discuss each of these components from the bottom up. And I'm not going to dwell on each of the components very heavily, but at the very bottom is the CRC32 checksum scheme, and we have a random number generator, pseudo-random number generator built on top of that, which is called Zoshi-Row 256. It's a standard algorithm. We have the random sampler, the degree chooser, and the fragment chooser, and I'll explain all of them briefly here. So because CRC32 is only 4 bytes, it's very compact and can be included in the QR codes, which is why we chose it as opposed to something much bigger like SHA-256 or something like that. Because it's enough for our purposes to verify the integrity of the message. And so in our case, you'll see throughout this document, we're giving a small fragment of code and immediately after that, the test vector. So again, you can think of this is Swift, but you can think of this as pseudocode. And as we get into more complex parts later, you'll see that it's very heavily very heavily commented. So I just said CRC32. So why do we need SHA-256? Well, we do need to seed the random number generator. And the Zoshi-Row 256 ** PRNG needs a 256-bit seed. So we can actually use SHA-256 to stretch that CRC32 to a 256-bit seed. And so we have a test vector. We're assuming you're using an existing implementation of SHA-256. Now we're discuss the Zoshi-Row 256 ***. And it's this algorithm has public domain status. It's simple to implement. It's fast. It uses a 256-bit seed and has very high quality that is very statistically random output. It's not a cryptographically strong PRNG, but it's not actually a requirement for MUR to be that because we're not actually encrypting anything. So in this case, we actually give our implementation of Zoshi-Row and then several test vectors that you can basically implement to prove that you've got the same implementation. So built on top of that is the random sampler. And you'll see why in a minute, but this uses in the process of deciding how many fragments to mix together in each part, which may include many fragments, but it's biased to include fewer. And then we discussed the method we're using and the implementation we based our implementation on. Those are all there for your reference if you need them. But we've basically made it so that our random sampler, the random numbers it generates, come from the PRNG. So that because we're basically creating a deterministic system here, a consensus system between sender and receiver. This system does use floating point numbers. We had a few people say, well, but about floating point error? Won't that, cause different problems and different problems? So we actually address that here. Although this algorithm does use floating point numbers, as long as the implementation is running on IEEE 754 compliant platform and the PRNG returns deterministic results, the result of this algorithm will also be deterministic. So it's required that the implementation of this random sampler use the IEEE 754 floating point numbers. This is basically every processor in existence now. If you can show me one that doesn't use IEEE 754 that isn't a relic, I'd be very surprised. And any problems you ever heard of, like the Pentium bug and so on, those have long since ceased to be issues. So we do not expect this to be a problem at all. So there's the implementation of that, and then the test vector. So determining fragment length. The encoder first partitions the message in fragments of equal length, and there's no single right way to do this. And we discuss here at some length what the considerations are, how fast you want to display them, how dense you want them to be, the resolution of your camera, the resolution of your display. There's no one right way to do this. And so ultimately, this is up to you to decide your fragment size for a particular transmission. Our reference implementation is, has a specific methodology. The linear search to find the largest fragment length that for a given message length produces the least number of fragments that lie within the given minimum and maximum fragment length. So that's the way we're doing it. Yes.
Also, to be clear, we've tested this fairly thoroughly on LeafyKit at the low end, which is a low-end ARM device with a display that is only 200 by 200 and has a high latency in the pixels being changed because it's a paper ink display. Works with MUR. But we've also, on an iPhone, fairly high-powered device, big display, really good camera, etc. We've seen very, very high throughput, iOS device to iOS device. So we support a wide range. Obviously, every app is going to be different. Sparrow, for instance, runs on laptops. Laptop cameras are notorious for, not focusing well or not having super high resolution. So
definitely
they
not designed for scanning documents.
Yeah. So they have to make different choices than another device does. That's, where all the trade-offs are is, what does your specific device support? What are your scenarios? But also like what other parties in the ecosystem are you interoperating with? So, if you're going to be using laptop's QRs, you might go very differently than you do than a current mobile device to mobile device.
Right. So then we provide some simple test vectors here, and then once you know the sec lane, then you need to generate the fragments. And if the last fragment would be smaller, because of course not everything works out to even multiples of your fragment length, it's pad with zeros at the end, and there's good reason to do that. But for now, just what this outputs is takes in a data and a fragment length and outputs an array of data objects. And then if the padding is necessary, it appends the padding at the end, and that's all that does. So we have test vectors for that. And again, this is basically using the our random number generator seed with constants, so the test vectors always succeed. All right, the degree chooser. So once we've chosen the fragment length, now we can choose the degree. Now, what's the degree? The degree is the number of fragments that are mixed in each package, and the degree is chosen pseudo-randomly with a bias towards lower degrees. The successive relative probabilities of higher degrees being chosen are our harmonic series: 1/1, 1/2, 1/3, 1/4. This is where this is the degree, and the probability goes down to 1/sec. The choices to choose a harmonic series is strategic. It bases the selection towards lower degrees. It biases the selection toward lower degrees, which is crucial because degree 1 parts or simple parts are essential in decoding higher degree mixed parts. And we'll talk about that more in a bit. This system ensures there are enough low degree parts, especially simple parts, to initiate and facilitate the decoding process. And this is the degree chooser is fairly simple. It's based on the random sampler. And basically, so it's given the harmonic series of probabilities based on seclen, and then every time you say choose degree and you give it the seeded random number generator, it gives you an integer back, which is the degree of the part and our test vector. So we need to choose which parts at this point. And so for this, we're using the Fisher shuffle, which is a provably random shuffle. But we've optimized it so that rather than shuffling all the part numbers and then taking like the leading 5, if it's a degree 5, then it just stops at the number of items you asked for. And our test vector showing the count here. Actually, this is not correct. I need to update that with the last version of the Fisher shuffle there. But anyway, so you can see that it's actually generating consistently both the number and random shuffles of the actual part lengths. There's yeah. So all right. So now the fragment chooser, and this is where it all comes together. The fragment chooser is initialized with the seclen and checksum of the message, and then that's used to pseudo randomly choose which fragments to include in each part by providing the secnum of the part being generated. So this is the means by which the sender and receiver agree on which fragments are included in each part. And that way they don't have to exchange a table. Here's the parts I haven't. They just know based on the checksum and the secnum. And the return value is a set of fragment indexes. And I won't belabor this too much, but we basically see the random number generator and using the secnum and the checksum, stretch that with SHA-6, seed the random number generator. And so the fragment chooser essentially, uses the degree chooser inside it. And when you choose the fragments, it basically says that, and this is the critical part, if the secnum is less than the seclane, then we're just returning the unmixed fragment. And that's why you have the hybrid unmixed fragments, because the unmixed fragments come first. And then after that, then what we're doing is we're basically creating our seeding the random number generator, choosing the degree based on that, and then shuffling, and then choosing only the degree count that we want of pieces and returning that as a set of fragment indexes. And you can see that fragment indexes is an alias for a set of integers. And our test vector. And so you can see that here's the fixed rate parts that come first. And then the rateless parts start, jumping around between simple parts, and some have a lot of them mixed in and some have a few mixed in, but they're biased towards the simple parts. All right, moving on to part serialization. This is how the sender and receiver actually communicate. We're using CBOR to do this, and this doesn't have to be DCBOR, but CBOR, it works out the same way. It's going to end up being, if you use the standard encoding methods of CBOR, it'll be DCBOR too, so it doesn't matter. We're using CDDL, which is the language used to describe CBOR structures here, and it's basically it's an array of five elements, and it's basically pretty self-explanatory here. We haven't discussed message len yet, which is conveyed in each part as well, which is the total length of the message in bytes, not including any padding, added less fragment. And then that basically translates to our reference implementation structure here, a more detailed walkthrough of the actual meanings of these, and then our test vector. And this is just syntax highlighting stuff, because we're showing we're showing the diagnostic output of what the CBOR is, which is the human readable form of CBOR. So you can actually see what's been encoded in this, and syntax highlighter doesn't like it for some reason, but it is totally valid Swift. All right. Next is the buffer XOR primitive, and this is really straightforward. Just, hey, give me two buffers of equal size and XOR them together, give me the result. And that's all that really is with a test vector. And then now we're talking about the encoder, and the encoder and the decoder are very interesting, because the encoder is actually pretty simple compared to the decoder, but the decoder can sound kind of scary at first, because you're receiving these parts which are mixed together with the XOR, and what do you do about that? How do you put the spaghetti back into the package once it's cooked? So yeah, but it's actually not that bad. So basically, I talk about the initialization of it here, and basically show the state of it here, and it's but basically it comes down to every time you ask it for the next part, increments the sequence number. If it's a single part generation, don't call this again. It uses the fragment chooser to choose the fragments. It mixes them together and then returns the part. That's it. Okay, it's really simple. And we've already talked about the fragment chooser. This is the actual function that does the mixing. If it's only one fragment, it just trivially returns the fragment. Otherwise, it mixes them together using the XOR function. So you see, again, everything we're doing here builds on what's previous. And then we have test vectors for this. This outputs the actual kind of debugging output of this, again, using deterministic message. And then also we are testing the CBOR output. We're not, since CBOR outputs can be, primitives are going to be different on a different platform, we're not providing code for that, but it's in our reference implementation if you want to go see how we did it. But you should be yielding this output for that. And then also testing to make sure that the encode says it's complete when it says it is. All right, now onto the decoder, because the encoder, like I say, is simpler. The decoder requires a little bit more understanding. And so I want to make sure people understand this. And so we have an essential decoding concepts here. So fountain codes may be simple or mixed. Simple codes contain exactly one fragment. Mixed codes contain two or more fragments combined with XOR, and we're using the circle plus operator for that here. So let's say we have we wish to transmit a message A, B, C, D, which we partition into these fragments, and the lexicographic order or alphabetical order of the letters represents each fragment's secnum. So this is 1, 2, 3, 4. Each part is also transmitted with the second of the message, which we'll gloss over here. So the decoder keeps track, keeps three basic structures: a list of mixed parts that it hasn't been able to unmix yet, a list of simple parts that it has managed to reduce, and a queue of parts that still need to be processed. And these are initially empty. So in our scenario, it first receives the A, B, and C mixed together. And it knows that, so all it knows about this part is how many fragments there are in the final message, because seclen is transmitted. So it knows there's 4 parts it's going for, 4 fragments it's going for, and which 3 this part mixes, A, B, and C. But it can't know actually extract anything yet because they're all XORed together. So, the next part receives is C plus D, or C XOR D, and it still can't extract anything from that because there's no way by XORing these two together that you get anything that is smaller than what you have currently. So it stores that as well. The next part receives is A, B, C, D. Wow, it seems like it's getting worse, but it's actually getting better. So each time a part is received, the decoder checks to see whether the set of fragments it contains is a proper subset or superset of the set of fragments in any part it already has received. If so, it can reduce the superset part by the subset part. In this case, it discovers that it can reduce the incoming part, A, B, C, D, by XORing it with part A, B, C, yielding the simple part D, because it's going to think about subtraction. A, B, C, D minus A, B, C is just D. Wow, okay, we've recovered a fragment. The reduced part, D, now goes into the list of simple parts that have been received. When this list is complete, the entire message can be reassembled and decoding will be complete. The reduced part also goes back into the queue of parts, take part in reduction. As long as this queue is not empty, it takes the next item from the queue and continues looking for parts that can be reduced. We don't even get a new part from the stream yet until we've done that process, until the queue is empty. So we're going to take D out of the queue now, and it now discovers that it can reduce part 2, C and D, by part 3D, yielding the simple part C. So without even receiving another part, we've already recovered another fragment. So the reduced part is moved in the list of simple parts and also back to the queue. So we take C from the queue and discovers that it can reduce part ABC to part by part 2C, yielding the simple part A and B. This reduced part is still mixed, and we can't do anything more about that. So it stays in the same list in its reduced form, and it's put back in the queue. When we take that from the queue, well, we can't do anything with it. So we're now done with the queue, and now we go back to the stream. And the next part that arrives happens to be A and C, and it can reduce this part by C, yielding simple part A. So we have now 3 out of 4. Puts this back into the list of simple parts and into the queue. We take A from the queue and discovers it can reduce A and B by by A, yielding B, and that's it. Okay, the original message is now assembled by sorting the parts by secnum, represented here by the letters lexicographic order again, and concatenating their fragments to yield the original message. Now you understand how list fountain decoder works. It's really actually very straightforward. So, so how to represent parts in the decoder? So there's the fountain encoder part, which you've already seen. That's what we were serializing in the CBOR. And that it's the output of the fountain encoder, but also the input to the fountain decoder. And because it also supports serialization to and from CBOR. Internally, fountain decoder has its own fountain decoder.part struct, which it uses to track the simple and mixed parts it's processing. And as you can see, all it has is the fragment indexes, which is a set of integers for a reminder, and the data. That's the only data it tracks. And then it has some initializers and convenience methods like, is this simple or not? So the decoder state. Remember, we've already talked about this. Simple parts and mixed parts are dictionaries of parts it's received, and then there's a queued parts. So we're just implementing what we described. You don't initialize it with anything because all of the state is set to empty. When the first part arrives, it's going to basically set everything up as setting the stage for all the other parts to arrive. And then basically there's a result attribute, and you can see that here, which is essentially it's either going to be null, which it is at the beginning, which is denoted by the question mark, or it will be the resulting data or an error. And there's only really one error that can be thrown, which is the final checksum didn't match. So because any invalid parts that come in are just discarded silently. And if you use the UR demo, you'll notice that if you try to read part of a UR sequence and then try to read another part of a different UR sequence, it'll click because it's throwing away those parts. It doesn't recognize them. You can go back to the original UR sequence. It continues. So it doesn't blow the whole decode to receive invalid parts. So here's the actual dictionaries. Part dict and a part dict is essentially keyed by fragment indexes and a part. So this is the decoder part. So validating incoming parts. So as each part is received, the first part is assumed valid and sets the values for all subsequent parts that match to be valid. If any part does not match these values, it's discarded. And it says what has to be matched. And then if it's valid, it returns true and false if not. So here you see it's basically checking to see, do we have we gotten a first part yet? If not, then we set everything up based on that first part. Other than that, we check everything as that first part, and if anything doesn't match, we throw away the part. So part reduction. This is a very simple algorithm actually, because it takes two parts and tries to reduce part A by part B. And that basically means that it checks to see if B is a strict subset of A. That means, B can be subtracted from A. And so if it can't, then it just returns A by itself. If it can, it actually does a set subtraction, subtracts the fragment indexes, and then sets the new data to AX or B. And that basically reduces the fragment. And so you're going to see how this is repeatedly used over and over again. So reducing mixed parts. So remember that list of mixed parts. Anytime there's a new part to process, we're going to try to reduce all the existing mixed parts we're tracking by the new part using the reduced mixed method, which is what we have here. Any resulting simple parts are added to the queue, and the remaining mixed parts are kept in the mixed parts list. So that's all that's happening here. We're going to the mixed parts, trying to reduce them. Then we're creating a new mixed parts list with everything that's possibly reduced. If it's been reduced to simple, we can queue it. Otherwise, we just add it to the reduced parts list or the new mixed parts list, and then finally we assign that back to the original list. Simple parts are handled slightly differently. They're processed by this method. If the part's a duplicate, it's discarded. If it's not a duplicate, it's added to the list of simple parts, and the set of received fragments is updated. If the set of received fragments is now equal to the set of expected fragments, we're done. Message is reassembled and the checksum is verified. So here you basically see, we're throwing away duplicate parts. We're recording this part, checking to see if we received all the parts, verifying the checksum if we have. If not, we're doing the reduced mixed, which you just saw above. And then processing mixed parts. So if we receive a mixed part, again, we discard it if it's a duplicate. That's if it's already in the mixed list. If it's not a duplicate, then an attempt is made. This is important because this is where we have, both the subset and superset, all the parts try to reduce each other. An attempt is made to reduce the new part by all the parts we're currently tracking simple and mixed. If after the reduction the part is now simple, then it's added to the queue. If it's still mixed, then an attempt is made to reduce all the mixed parts for the new part, which you've already seen. That's called the reduced mixed here. So don't process duplicate parts. Here's the concatenated list of all the simple parts and all the mixed parts. Then we'll reduce the part, and then basically record what we did. Now at the higher level, remember I talked about processing the queue. When the queue basically has anything in it and we're not done, then we get something from the queue and we decide if it's simple, and then we call one of the two methods above to process it, and just repeat this until either we finally come up with the solution to the whole problem, we reassembled the message, or the queue part's empty. So you see we're getting to higher and higher levels here, and we're almost done now. So finally, the receive part method is called to submit an incoming part to the decoder. It returns true if the part was processed and false if it was discarded. The part is discarded if the decoder is already done or if the part is invalid. When receiving the first part, a fragment chooser is initialized with the seclan and checksum from the part, and the fragment chooser is used to choose the fragments into each part in agreement with the fountain encoder. So again, this is the consensus stack. Once incoming parts fragments are known, the part is added to the queue, and the queue is processed until the message is complete or the queue is empty. So here you see the implementation. Don't process the part if we're already done, because we're done. Don't continue if this part doesn't validate. So we can discard it at this point. If this is the first part, then it's going to set the parameters for everything else. If we don't have a fragment chooser, now is the time to create it. And then we add this part to the queue. We choose the fragment and the part. We discover basically which fragments are in this part by using the consensus stack, and then we queue that part. We process everything in the queue because, as you saw, processing a piece of the queue can add more things to the queue. For bookkeeping, we keep track of how many parts we're doing, and then we return true. And this is the test vector, and that's it. And I know that was kind of long-winded, and hopefully, somebody viewing this later will think it was worth the time stepping through it. But I wanted to show that this isn't scary at all. It's actually fairly straightforward to implement. All the test vectors are there. You can see why it's already been implemented on several other platforms, and we're basically enthusiastic about people adopting it further. It's one of our best success stories so far, and we think it's going to be used in a lot of different ways that we're not even imagining yet. And like I said, this is separable from the whole UR implementation. So if you want, for some reason, a good way of transmitting data through a lossy channel, this is actually, I think, a pretty good way of doing it without even using the higher level UR textual encoding. Any questions?